Okay, now we're going to see how we can use the normal distribution as an approximation to the binomial distribution. Now, the requirements are first that the sample is a simple random sample of size n from a population in which the proportion of successes is p, and the sample is the result of conducting n independent trials of a binomial experiment in which the probability of a success is p. Right? So the second requirement is that n times p is greater than or equal to 5, and n times q is also greater than or equal to 5. Okay, now the normal approximation, what we're going to do is we're going to use the mean of our normal distribution is going to be the mean of the binomial distribution, which is n times p. So the mean that we're going to use for our normal distribution is going to be n times p, and the mean that we're going to use for our, or sorry, the standard deviation that we're going to use for the normal distribution is what we get when we take the square root of n times p times q, the standard deviation of the binomial. So we're going to assume that the mean of the normal distribution we're using to approximate the binomial is the same as the mean of the binomial, and also the standard deviation. All right, now the continuity correction. When using the normal approximation, adjust the discrete whole number x by using a continuity correction so that x is represented by the interval from x minus zero point 0.5 to x plus zero point 0.5. So we have, oops, let's see, we have a value x. We have this value that we're calling x, and we're looking at x on a number line. We have this value x, and it's a discrete number, because remember the binomial is a discrete distribution, but the normal distribution is continuous. So what we have to do is we have to represent the discrete whole number x with an interval of values, ranging from x minus oops, ranging from x minus zero point 0.5 to x plus zero point 0.5. So this single discrete value of x would be represented by the continuous interval from x minus zero point 0.5 to x plus zero point 0.5, and that's called the continuity correction. When we use the normal distribution, which is a continuous probability distribution, as an approximation to the binomial distribution, which is discrete, a continuity correction is made to the discrete whole number x. The binomial distribution, by representing the discrete whole number x by the interval, and that's exactly what we're just talking. We add and subtract zero point 0.5 to x. So here is an example of how we use a continuity correction. Well, we have um, Mendel's hybridization experiments. When Mendel conducted his famous hybridization experiments, he used peas with green pods and yellow pods. One experiment involved crossing peas in such a way that 25% of the 145, um, or sorry, 25% or 145 of the 580 offspring peas were expected to have yellow pods. So of the total 580 offspring, we expected 25% of that, 145, to have yellow pods. Instead of getting 145 peas with yellow pods, he obtained 152. Assume that Mendel's 25% rate is correct. So we're assuming that the correct proportion P, um, of uh, yellow offspring, yellow potted offspring, is going to be 0.25. That's what we're assuming here. And what we're doing is we're looking at the 580 as being the size of our sample, 580. And let's see, x is 140, sorry, x is 152. X is equal to 152. And actually, let's see, what do we have here? We need to find, let's see, find the probability that among the 580 offspring peas, exactly 152 have yellow pods. So what we need to do here is we need to apply the binomial with n of 580, p of 0.25, and x equals 152. Now that calculation would be quite cumbersome. So what we want to do, well actually it's not that cumbersome, this particular one, for part A. What we want to do is find the probability that x is equal to 152 of exactly 152. So we want to find the probability that x is equal to 152. But that's a discrete whole number, and the continuous normal distribution, the probability of any discrete whole number is 0. So we have to convert this discrete number to an interval, and we're going to change it so that we're actually looking at the interval that where x would be somewhere between 151.5 and 152.5. So that's the interval that we're going to use for our continuity correction. The number 152, 152 on a number line is being represented as the interval from 151.5 to 152.5. So we're using that interval to represent this discrete number. All right, so that means what we need to do then is we need to go to our normal distribution, and we need to find the mean and standard deviation of this normally distributed random variable. Sorry, we need to find the mean and standard deviation of this binomially distributed random variable and use those as approximation to mu and sigma for the normal. So the mean we already have is 580 n times 0.25, which is p. N times p in this case was already given as 145. So the average, the mean, is 145. The standard deviation is equal to the square root of n times p times q, which is the square root of 580. Oops. Square root of 580 times 0.25, 580 times 0.25 times q, which is 1 minus 0.25, the complement of 0.25, 0.75. So this is how we're going to find our standard deviation. Let's go ahead and find that. Let's see. So we have the square root of 580, oops, 580 times 0.25 times 0.75, n times p times q, and we get that this is equal to 10.4. So we have 10.4 as our value for sigma. So the standard deviation is 10.4, and the mean is 145. And what we have to do is we have to find the probability that x is a number between 151.5 and 152.5. So we're going to go ahead and we're going to set up our bell curve. And what we have is we have here a bell curve with a mean of 145, and the x value that we have is the value of x. The values of x are 151.5 and 152.5. So 151.5 is up here somewhere. 151.5, and we also have 152.5, 152.5. And what we're doing is we're looking for the area in here, right? Because that interval is representing the number 152. So we're going to convert those two numbers to z-scores, and then we're going to find the area. Actually, we can use the normal CDF in a different way. We're going to put these parameters into the normal CDF function. We're going to write the normal CDF, and we're going to put, instead of the left z, we're going to put the left x, comma, then we're going to put the right x, comma, then we're going to put the mean, comma, and then we're going to put the standard deviation, and then we're going to close our parenthesis. All right, so those are the parameters that we're going to put in to our normal CDF functions. So that's left x value, right x value instead of z. So this is a bit of a different way of using that normal CDF function. All right, so let's go to the normal CDF. We're going to go to second. Oops, turn it on first. Clear. Second, we're going to go to distributions, and we're going to the normal CDF, which is number 2. And instead of just putting in the left z-score and the right z-score, I'm going to put in the left x value, which is 151.5, comma, the right x value, which is 152.5, and then I'm going to put in the mean, which was 145. Oops, 145, and the standard deviation, which was, oops, got the standard deviation there. Standard deviation was 10.4. So the standard deviation is 10.4. And I close my parenthesis and I press enter. And I get the value 0.030 or 0.031 actually. So it turns out that this area here is equal to 0.031. 0.031, and that corresponds to the probability at 0.031, right? That corresponds to the probability that we get exactly 152 babies. So the probability that x is equal to 152 is approximated by the normal distribution as 0.031. And now for part B, we want to find the probability that at least 100 and what was it? At least 152. 152 are yellow pods. And this is the probability that the variable x is greater than or equal to at least 152. And what we're going to do here is when we draw our bell curve and we want at least 152, well, once again, the mean is 145. And we're out here at 152, and we want to be at least 152. So we want to actually include that number, that discrete whole number 152. If so, what we're going to do is, instead of using the discrete whole number 152, since we want to include it, we're going to go back by 0.5 and include it by looking at the number 151.5 instead, and looking at the area to the right of 151.5, because we actually in this case want to include the 152. So we would go to our normal CDF, normal CDF, and we would put in the parameters. Well, the left x would be 151.5. The right x would be E99. The mean is again 145. And the standard deviation, what was that again? 10.4. Let's make sure there. 10.4. The standard deviation is 10.4. So we're going to plug those numbers in here to the normal CDF and get an approximation for that binomial probability. So let's see here. We have, let's turn it on again, clear, and then we'll go to second, distributions. We're going to the normal CDF, which is number 2. We're going to plug in 151.5, comma, second, and then we're going to do E99, and then we're going to do comma. The mean is 140, oops, 145, and the standard deviation is 10.4. Close the parenthesis and press enter, and we get that this probability is 0.266. So this is 0.266. So we have the probability that x is greater than or equal to 152, or at least 152, is equal to 0.266.